Okay, so welcome back. As was just noted in chat, yeah, so the most recent announcement um, uh, listing out the lecture and uh, as well as letting you know that homework 6 has been extended, so you can have a read at that. Basically, it's an indefinite due date, so just turn it in whenever you have time. Okay, so um, what is the deal? Last time uh, we had basically completely gone through our uh, full extension of the Mobius transformations, or of linear fractional transformations to Mobius transformations. And so for linear fractional transformations, we had invariants, right? We're wanting to use these transformations to figure out what geometry results. And part of that is, remember, kind of the key thing was that these invariants tell you what should be important to you in your geometry. So if you study the transformations have certain invariants, so things they preserve. And the things they preserve are important for the same reason that the things preserved by isometries in Euclidean geometry were important. So isometries in Euclidean geometry, imagine you started with those, right? So you started with, say, plane isometries, so isometries of R2. The things that those preserve are things like length, angle, um, notion of, say, congruence for triangles, right? Which ultimately comes from length and angle. But so really, like, length and angle are two big examples immediately that pop out at you. And so for Euclidean geometry, we're studying those Euclidean isometries. And so following the Klein point of view, this tells me that the reason why length and angle are important is because they are invariant with respect to those Euclidean isometries. So what was invariant? What was an invariant of the linear fractional transformations? Well, straightness of lines, right? Straightness of lines is invariant, right? Collinearity. Uh, but well, what else? Well, the big major invariant, of course, is the cross ratio. So the invariant was the cross ratio. This was the big one, right? The problem with the cross ratio is that it can be hard to see what is going on with the cross ratio geometrically. And so this is one of the reasons why we moved from RP1, right, to upper half plane. So for the upper half plane, we have Mobius transformations. Right, so we've extended these things now. So our Mobius transformations, of course, the main difference here is that whereas we use the generating transformations to understand what was going on for linear fractional things, we use slightly different generating transformations, right? The extension of these generating transformations to understand what's going on here. So we're going to do that throughout class today, basically. And so what are the invariants? So it turns out that the invariants are preserving lineness. That is, the things that we call lines for Mobius transformations are preserved. Okay. And it also preserves non-Euclidean length that I'll call length with quotation marks, but this is an honest-to-God length in the sense that we would want anything calling itself length to satisfy. Okay. And so we're going to do both of these today. If we finish this by the end of class, then we'll be happy. Okay, so we want to show that these are the invariants of these Mobius transformations. Okay, so to answer number one, I define lines in my upper half plane, right? So the lines in my upper half plane as described previously are either vertical lines or semicircles with centers on the x-axis. Okay. So I have two types of lines, vertical lines or semicircles with centers on the x-axis. So of course, the first time we mentioned this geometry, the upper half plane, this was my definition. But now I'm going to show like why it makes sense to call these things lines. Okay, there is if you think we're just cheating by calling these lines and then like defining or like noticing all these properties they have and say, hey, like, you're just calling these things lines because that allows you to say that, say, the parallel postulate is false in this space. But there's a real reason why we're not cheating by doing this, because when we consider more general types of geometry and stuff that's a little bit beyond the scope of the course because it requires some more background, basically there's a way to set up a map, so a function that takes you from, say, this geometry, the upper half plane, and it maps this to the Euclidean plane, and it turns out that the lines in our non-Euclidean space, what we're calling lines, get mapped to Euclidean straight lines under this map. Okay, and so this is telling us that these things that we're calling lines are actually really the things we should be calling lines. Okay, and I'll mention that a little bit more, probably on the last day of class is when I would get to that. Okay, this is known as the Beltrami approach or Beltrami model. Okay, so I'll talk about that a little bit later. Anyway, so we want to see that non-Euclidean lines are preserved. So recall that we saw that any such line satisfies, so any such line, but I'm going to stop using this, okay? So I'm going to stop using line in quotation marks. We're going to call them just lines, okay? Since we're in our upper half plane, it's clear that the lines we're talking about are not Euclidean lines unless they're specified to be normal Euclidean lines. Of course, if they're vertical lines, they're already just normal Euclidean lines. Okay. So recall that any such line satisfies the equation. So we found this out last time. So the equation in question is A Z bar. Okay, plus, that bar goes a little bit too. There we go. So A Z bar plus B times Z plus Z bar plus C is equal to 0. Okay, for some A, B, and C real. Okay. So this is my equation of a general line, right? And we saw how we can make this work, right? Which things need to be zeroed out to either have a vertical line or a semicircle, right? Okay, we'll call this equation star. All right. Okay. There's equation star. So any such line satisfies this. Now, what do I want to prove? So my big fact. Okay, I won't even write it as a theorem. It's just a nice fact because the statement itself is the name of the theorem. Okay, so each Mobius transformation of the half plane. So each Mobius transformation of the half plane maps non-Euclidean lines to non-Euclidean lines. And so going back to what I wrote on the first page here, what I wrote was we were trying to investigate what the invariants of Mobius transformations were on the upper half plane. And so being a non-Euclidean line is an invariant, right? Lineness is an invariant in this sense because if you're a non-Euclidean line, Mobius transformation takes you to some other non-Euclidean line. Okay. And so what I'm saying is that you start out as either a vertical line or a semicircle with your center on the x-axis. You apply Mobius transformation. You either go to a vertical line or a semicircle with your center on the x-axis. Okay. And so we look at generating transformations. So to prove this, consider generating transformations for the Mobius transformations. So recall what those were. So the generating transformations were the horizontal translation, so Z gets sent to Z plus L. The positive dilation, so Z gets sent to KZ for K bigger than 0. There's the reflection. Oh, Z gets sent to minus Z bar. Right, that's reflection across the y-axis. Okay. So for these, it is easy to see since each of these is actually, consider what kind of transformation these are, right? So this is dilation, so it's not a Euclidean isometry, but the other two, so this is a Euclidean reflection. This is a Euclidean isometry because it's just a translation. So these two are Euclidean isometries, and so what I'm going to say is obvious. This is a scaling, so you just think about what this does, and what I'm going to say is obvious. So this is easy to see since these all map Euclidean lines to Euclidean lines. And circles to circles. Okay, better than that, and the x-axis to the x-axis. So this is key, right? Just sending circles to circles isn't good enough because you need to be able to go from a semicircle or circle in this case. So since semicircle is just part of circle, you need to be able to go from circle with its center on the x-axis to another circle with its center on the x-axis. And so what this is telling you is that this maps circles with their centers on the x-axis to other circles with their centers on the x-axis. Okay, why? Well, the first one is just horizontal translation, right? Okay, and so what's important here is Euclidean lines get mapped to Euclidean lines, but more importantly, vertical lines get mapped to vertical lines, right? So these all map, forget about Euclidean, these map vertical lines to vertical lines. Okay. I mean, the statement is true, which is why I barely marked it out. But these map vertical lines to vertical lines. Okay. All right. So the reason why is this is just a horizontal translation. So this is just Euclidean translation. So this works. So this is just horizontal translation of the half plane. Z to KZ, where K is positive, is dilation of the half plane. And the last one is just Euclidean reflection across the y-axis, right? This is just Euclidean reflection across y-axis. Okay. And so these things are very easy for us to figure out what's going on here, right? So vertical lines get sent to vertical lines, okay? And circles on the x-axis get sent to circles on the x-axis. So in particular, semicircles on the x-axis get sent to semicircles on the x-axis. So these three generating transformations obviously satisfy this fact of mapping non-Euclidean lines to non-Euclidean lines. It's even nice. They keep them in the same class of lines, right? Vertical lines go to vertical lines, semicircles on the x-axis go to semicircles on the x-axis. Okay, so that's nice. We have one more generating transformation to show, and then we'll be done, right? Because every Mobius transformation is generated from these three plus one more. That's inversion, right? And so this is the last one we have to figure out, right? Thus, all products of these transformations preserve non-Euclidean lines. Thus, we only need to check inversion. So we only need to check inversion. So Z getting sent to 1 over Z bar. All right. If this thing preserves non-Euclidean lines, then we're done. Okay, because any product of all these generating transformations does, which means any Mobius transformation does. So then that's what we're trying to prove. Okay. All right. So this is all I want to show. I want to show that this preserves non-Euclidean lines. This one is not as obvious as the previous three, and so I need to make use of referring to my equation. So maybe I'll do this on one page so you can see it and I don't have to keep flipping pages. So we do this by referring to equation star right on the previous page. So let me, like I said, let me actually write this out on one page so that it's easier to follow. So this equation star that we were talking about is the equation of a line in our upper half plane. So A times Z bar plus B times Z plus Z bar plus C is equal to 0. This is our equation star. Okay, so any non-Euclidean line satisfies this, right? So so then given a non-Euclidean line with equation star, that means any point on this non-Euclidean line satisfies star, right? So any point on the line satisfies star. Okay, so any point on the line satisfies this. So we want to find an equation satisfied by points of its reflection in the unit circle. So we want to find an equation satisfied by points of its reflection in unit circle, i.e. after being transformed by this generating transformation. This sends Z to Z 1 over Z bar. Okay. All right. But what do these points look like? So these are points. So these points are W's, and these W's, right, look like 1 over Z bar. Right. And in that case, W bar would be 1 over Z. right? And we would expect for the equation we get to involve both W and W bar, since our equation for a line, whenever you're talking about a point Z on that line, the equation involves both Z and Z bar. Okay. So these points look like this. How do I find such an equation? It's actually simple. I can just divide the equation I started with by Z bar. So divide star by Z bar. What does that give me? So that gives me an equation A plus B times 1 over Z bar plus 1 over Z plus C over Z bar is equal to 0. Okay. But actually I can rewrite this, right? I can rewrite this as rewriting and rearranging. This is C times, if W is 1 over Z bar and W bar is 1 over Z, this is C times W bar plus B times W plus W bar plus A is equal to 0. Okay. Thus, any reflection W equals 1 over Z bar of a point Z satisfying star satisfies the equation. I'll call this double star. Okay. But what is this equation? This is just a different equation for a line, right? i.e., it satisfies an equation of a non-Euclidean line. This has the same form as star. And so, whatever inversion has done, it has at least mapped a non-Euclidean line to a non-Euclidean line. Now, the nice thing about this is understanding it from the generating transformations also lets you deal with Mobius transformations generally by saying, well, if your Mobius transformation doesn't actually involve an inversion, then it sends vertical lines to vertical lines, semicircles to semicircles, so it actually like separates the line classes, but inversion mixes them. So inversion can send and will typically send vertical line to semicircle and semicircle to vertical line. Okay, and so that's why our statement was not that it preserved them in that sense, but it sends non-Euclidean lines to non-Euclidean lines. Vertical line could get mapped to a semicircle and vice versa. Okay, in fact, that's what inversion does typically. Okay, all right, and so we have this fact. Now, if you want to see what goes on here, right, so here's a great example from the exercises. Your final homework will involve some basic stuff on Mobius transformations. So here's an example from the exercises to show what reflection of the line x equals 1 looks like in unit circle. So unit circle is the not as bold semicircle here. Here's unit circle. So if I reflect the vertical line x equals 1 in unit circle, what do I get? I get this semicircle here. So this inversion in unit circle sent the line x equals 1 to, that's a vertical line, to the semicircle here. Okay. All right. Okay, so thus we've shown that Mobius transformations preserve non-Euclidean lines. Okay, so non-Euclidean lines are preserved by Mobius transformations. Now, the other thing I mentioned was a length. Okay, we'll get to that, but there's something I didn't mention that is also important, and I'll bring up now. So a little aside here. Mobius transformations also preserve angle and length. Okay, so I didn't mention angle before. Okay. All right, so to see that Mobius transformations preserve angles, so let's look at angles in the upper half plane. Now you might say, well, the upper half plane, it's like a part of the Euclidean plane, so why can't my angles just be the normal angles? Well, angles are defined to be, these quantities between lines, right? So lines have to intersect before you can talk about angles. So the fact that our lines are not Euclidean lines means that there's something we have to say here, right? And so basic question is, how do I define the angle between non-Euclidean lines? Because there's an issue here, right? If I have two distinct vertical lines, they don't intersect, so I'm not going to talk about angle at all. And so kind of the only case I can talk about is a vertical angle or a vertical line and a semicircle, or two semicircles, right? So that is taken care of by the following picture. So the answer is I consider angles between tangent lines. Now, the second that I bring in tangent lines, this definitely, might worry you because this means that the computations might get nasty. We can avoid most of the nasty stuff, but I'm actually still going to gloss over some of the computations here. So here's the picture that shows you what's going on. So consider the following lines. So one line is the unit circle. Okay, I have a vertical line L, and then I have a reflection of my unit circle across the vertical line L. That's one way of looking at it. As it turns out, if I look at these three lines, C, L, and M, these three lines are pairwise reflections of the third. Okay, so any two of those are reflections of each other in the third non-Euclidean line. So C and L are a reflection of each other in M. L and M are a reflection of each other in C. C and M are a reflection of each other in L, and so on. Okay, so any two of those are reflections of each other in the third. All right, but in this case, so look at this. I have vertical line meeting two other non-Euclidean lines. So they meet at this point. At this point, I don't need a tangent line for my vertical line. I draw in my tangent lines to those circles at that point. And what I get is at this point, the plane is split into 6 equal parts in this case. So each angle is pi over 3, right? 2 pi divided by 6. There's 6 of these. They're equal. So 2 pi divided by 6. Each angle is pi over 3 here. Okay. All right. So each of these angles is pi over 3. So this is how we're going to define the angles between between two lines. So I have three lines here. So what if L wasn't here? What would be the angle between M and C? I draw these tangent lines. The angle between them is going to be this larger angle here, which is going to be 2 pi over 3. Okay, would be the angle between them. All right. So that's the idea here. Okay, you might have seen something similar to this before. Okay. So now let's consider the effect of Mobius transformations on an angle in this way. Okay, so it turns out that we have the fact that Mobius transformations preserve angle. Okay, in this way. And I'm going to stop writing it with quotes here because, again, the second that if you assume that there's nothing wrong here with talking about tangent lines instead, these semicircles, these are nice, these are smooth, and I don't want to get into regularity concerns here, but everything that we want to do with these tangent lines is fine. And so once we've replaced them with tangent lines, well, now we just have a bunch of lines and you understand angles between them. So talking about angle is fine here. Okay, so Mobius transformations preserve angle is the thing. Now, again, the generating transformations, for most of them, it is easy to see that they preserve angle. Okay, and so we'll take a look at that now. So note the generating transformations that is the horizontal translations, the dilations, and reflection. These all preserve angle. Okay, because they're Euclidean, so these two are Euclidean isometries. So this one is not. Okay. So these two are Euclidean isometries. And since they're Euclidean isometries, they preserve Euclidean notions of angle, length, area, any kind of thing like that. Dilation doesn't. It's not an isometry. But dilation preserves angles. Dilation preserves angles. Right? In fact, it's kind of the key transformation that preserves angles, right? So think of similarity. Right? Think of what it means for triangles or other figures in Euclidean geometry to be similar to one another. Okay. So all these three preserve angles. So again, the culprit that we want to actually show preserves angles is inversion, right? So again, we need only check that the last remaining generating transformation preserves angles. But this is more complicated. Okay, if you think about what inversion is doing, of course, it's obvious why this is more complicated. And so let's look at this. So we think of this transformation, right, sending z to 1 over z bar. We think of this as being a combination of two transformations. So we think of this as two composites or products. So we think of this as two composites here. One is the reflection. Oh, my conjugate symbols, a little close to the z there. So we think of this as reflection, which we know is fine, and follow that with sending z to minus 1 over z. Okay, so it suffices to check a slightly modified version of this. So it suffices to check, since this one already does, this is actually just one of the previous reflections. So it suffices to check that this last remaining transformation, right, this weird like half of the inversion. So I mean, this is actually the inversion. This is just making sure that it matches up with inversion to unit circle. So anyway, it suffices to check this last transformation preserves angle. Okay. Now, this transformation by itself doesn't usually preserve Euclidean lines because it can map them to circles. All right, and so angle typically is talking about angle between tangents. Okay, so then the idea here, so the idea is use an infinitesimal view of angle. Since, okay, so the reason for doing this is, you know, the types of computations analytically that comes with the territory when you're talking about tangents, right, and derivatives. And so what I mean here by viewing an infinitesimal view of angles, since our angle is going to be typically angle between tangents, the idea is that, i.e., see what happens to the direction between points z and delta z, okay, when we send them to minus 1 over z and minus 1 over, sorry, not z and delta z, but z and z plus delta z, I should say. Okay, so see what happens to the direction between the points z and z plus delta z when we send them to minus 1 over z and minus 1 over z plus delta z. Okay. All right. Then we let delta z go to 0. That's the idea. Okay. Okay. All right. So what happens as a result of this, and I'm not going to go through the computation so that I can get to more stuff. So it turns out that this argumentation gets us there. So this argumentation works, and thus Mobius transformations preserve angle. Now, if you want to see that, I only omitted like a paragraph worth of computations here. This is page 187, 188 in the textbook. Okay, if you want to see what that looks like. Actually, I guess even better, I could just flash it on the screen. You could see exactly what it is that's going on here. So you can pause and have a look. So here's where the argument starts. Okay, and the finishing of the argument is here. So there's the computation part. You get this quantity here. Okay, after you let delta z go to 0, you find that the direction from those 2 points we were talking about is theta plus constant, And then this just requires some tidying up bookkeeping here to get exactly what you want. All right, and here's the end. Okay, that's a nice thing about online teaching is it's easy to get that kind of content to you. Okay. Now, this leads me to considering tilings of the upper half plane. Which is one of the, like aesthetically, this is one of the prettiest things that comes out of all of this geometry that we've been doing. In fact, so much so that it provides us with the cover art for this textbook. Okay, so the cover art for this textbook exactly comes from this. So what's the idea? Take a triangle with angles, say pi over p, pi over q, and pi over r, where p, q, and r are positive integers. So they're natural numbers. Okay. Okay. Then any reflection of our triangle will have the same angle measurements. So it'll have the same angles. Right? So reflected a bunch. Right? Remember that our non-Euclidean reflections allow us to reflect across these non-Euclidean lines, these semicircles. Right? Reflect a bunch. This generates a tiling of the upper half plane. What does that mean? So this tiling of the upper half plane is a tiling by triangles, right? So this is a tiling by triangles. Okay, if you're familiar with tiling of the plane, right, then you might be most familiar with tiling of a plane by regular polygons, so either triangles or squares or hexagons. And so you've seen that, of course, for Euclidean space. You've seen tilings. And of course, the first thing you might tell me as a description of those Euclidean tilings is that they're flat, which makes sense because Euclidean plane is flat. What do our tilings look like when we tile by triangles in our upper half plane? They look like this. So I've repeatedly reflected the same triangle. You can identify the reflection lines if you pick out one of these triangles. So there's my tiling by repeated reflections. And that's what it looks like. Okay, so if I pick one of these, so we'll say our beginning triangle is this one, right? So if that's my beginning triangle, remember a triangle is just a figure composed of 3 line segments. These are 3 line segments in our upper half plane. So that's a triangle. I start with that triangle and reflect it a bunch in different non-Euclidean lines. This is the picture I get. Going off forever towards the boundary and going off towards the far upper reaches of the upper half plane in that way. So this is a tiling of the upper half plane by reflecting a triangle. Note, this is the cover of the textbook. Okay. Now, other than just being a nice, pretty picture, what is this saying? What's one thing to note from this tiling? So notes about this tiling. First of all, what were the angle measurements there? For that one, the angle measurements, so angle measurements of the triangle angle measurements of the triangle are pi over 2, pi over 3, and pi over 7. So let me bring that up here. Now, why did we wait until now to give you this picture? Because I just said that Mobius transformations preserve angle. And I need that, right? Because without that, then there's no guarantee that I could tile the plane. If it doesn't preserve the angle perfectly, then I would get some mismatchings here at these vertices, right? The idea is that I can, because the Mobius transformations preserve angle, it means that all these are going to fit together perfectly because they're just reflections of the same starting triangle. Okay, and so what this says is that if I measure these angles here, and you could even draw in some tangents here to estimate, what those angles look like. The pi over 2 angles here, that's a right angle in our upper half plane. So the tangent is a horizontal line. The other line in question is a vertical line. So that's a right angle. So that's angle pi over 2. The pi over 3 angle is here. And the pi over 7 angle is at this last vertex. Okay, so those are my angles in this triangle. Now, the angle measurements of the triangle are pi over 2, pi over 3, and pi over 7. You might note, that pi over 2 plus pi over 3 plus pi over 7, whatever that is, if you just do some quick mental math here, whoop, I'm a little blurry. So if you do some quick mental math here, note pi over 2 plus pi over 3 plus pi over 7 is less than pi. Whoop, I didn't like that pi. Let me rewrite it. It's less than pi. All right, why is that a big deal? i.e., non-Euclidean triangles do not have interior angle sum pi necessarily. Okay. So typically for these triangles, their angle sum is going to be less than pi. Now there is a relationship they have. They are proportional, typically to angle sum minus pi, or pi minus angle sum. They're proportional, so they're the area of the triangle is proportional to that, I should say. But the these non-Euclidean triangles we've drawn here don't have interior angle sum pi typically. Okay, it's typically less than pi. All right. Okay. Another thing, 3. To create this tiling, we only used reflections. All right. So, our reflections that we use, of course, are more general than Euclidean reflections. Some of them are honest-to-God reflections in the sense of reflecting across a vertical line. Some of them are these inversions in circles or reflections across a semicircle. These preserve length that I have not defined yet, and I will on Friday. These preserve length, which means all of these triangles, I'll write it in caps, all of these triangles are the same size. Oh. Now, you might have me put same size in quotes here. I'm happy to do that. All of these triangles are the same size. Let me bring back the picture again. Okay. So they don't look like they're the same size clearly, right? Even around the same vertex, this triangle does not look like it's the same size as this triangle. Okay. Right. This triangle has the same area as this triangle. Right. And this triangle has the same area as this triangle. It has the same area as these. Oh, I was kind of off the screen there. So here, this triangle here. Right, so this triangle has the same area as this one. Right. Okay. This tiny triangle here has the same area as this one. Pick any two triangles you want, even these tiny little microscopic triangles down here. These triangles down here have the same area as these huge triangles up here. And of course, if we blew this up even further, doesn't matter how far I go out, pick any triangle you want to, those have the same area as these down here. Okay. Now this is one of the coolest parts about this type of geometry. And it's also one of the most perplexing or confusing because these don't look like they, should be equal in any sense, but they are in this geometry. And I'll start off next time with a discussion of this, how this is kind of like a perspective view of the Euclidean plane where this x-axis is our boundary. It's one of our boundaries off at infinity. Okay, and I'm looking at it from a certain perspective, right? So that's one way of kind of thinking about what's going on here. Anyway, I'm going to link a video before class Friday that shows you other tilings and other models of this phenomenon. And it's going to show things that are equivalent in some way to this upper half plane description. And it's going to show some really, really nice pictures. And then I'll link something else that's a really nice video on Mobius transformations. So anyway, I think that's all for today. So then on Friday, like I said, I will discuss the notions of length and also go over the very last bits about this. I'll go over the very last bits about this geometry. Things like every Mobius transformation is a product of three reflections and stuff like that. Okay, these are really nice facts. And it shows how this is almost Euclidean in some sense, but it's still not. Okay. All right, so I think that's it. As I said, there's extension for homework 6, so look at the announcement, and I'll post the grade column for homework 6 soon. Okay, and I'll post your homework 7 soon as well, and like I said, it'll have another indeterminate window. Our final exam I don't think is scheduled till the 21st, so as I mentioned before, I'll post it days before, and you'll have like 5-ish days to do it, so you'll be done with the course on the 21st. Because it'll be due on the 21st. And so I will post another announcement about that slightly later after these announcements so that it doesn't kind of get lost. So anyway, that's the plan. So I will see you all on Friday.